Hi again. I'm gonna show you a preview of what I'm calling Arduino Co-routines. And I'll just jump right into showing you first the high-level assembly language that I created in order to write the kernel for the coroutines task switcher. So here it is. Here's the context. I call it context switcher.asm. The name of my language is SHLA for Stefan's High Level Assembler. But I couldn't use .shla extension in platform IO and get it to do anything automatically, so I'm using the ASM extension. And I recognize, my compiler recognizes files of the correct type by looking at to see if they start with this type section keyword. But anyways, it's fairly structured in order to make it easier to compile, and this can all change in the future. I can make it a little bit more flexible, but right now I was just trying to get enough of the compiler and the language working so I could do the task at hand. So it's broken into three sections. A type section, the assembly files are broken into three sections. A type section where you make declarations of constants and externs and stuff like that. A data section where you declare your data, your labeled data locations. They would be equivalent to variables in a high-level language. And a code section where you have functions. So looking at the type section, I have some externs here for system functions that I'm going to call in the code, like malloc. I'm going to need malloc millis because I'm doing stuff with time. Free because I'm doing malloc, I need to do freeze. Serial is because I want to do IO. I don't know if I'm actually referring to that in this code because I think I took all the debugging print statements out. And this symbol is a mangled a C++ mangled name for the printf function that's available, serial.printf. But again, I think that this is from an old version. I'm not really using it. I have the ability, you can see here, a struct node. I have the ability to find something like a structure type where everything is word size, so they're all 32-bit words in this case. So I have like a struct that I can overlay on memory locations and treat it like a C++ or a C struct, where they're only able to be of word, 32-bit word type, uint32Ts. So I don't bother giving a type for each of the entries in the struct, but for my coroutines, I track, I call it a node, and I track the coroutine state in these nodes. I have their stack pointer that I need to save when I put them to sleep. I have a pointer to the lowest end of their stack, a pointer to the highest end of their stack, which would be their initial stack pointer, state, which is their current running state, a wake up parameter so they can go to sleep for various reasons. So I have a 32-bit number to indicate the parameter for when to wake them up. The this pointer, so my coroutines in C++ land are actually C++ classes So the pointer to the objects of those classes, I keep track of that for doing some bookkeeping. Also for access to their methods. A next and a prev, because these nodes are going to get linked into a doubly linked list, so I can have a list of active, the currently active coroutines. And then I have constants. So I'm just really going over language features here, not really how the coroutine task switcher works, but I can declare numeric constants, like for my different running states. I've got not started, running, waiting, and they each have a numeric value that I can use as a constant in expressions when I'm loading registers with these constants, or storing them out, or comparing them. So I can have constants. And here's a couple more externs. The data section, everything is word sized at this point. So I have these variables that I use to track the state of the kernel. And this is basically just allocating storage in the data segment. In the code section, I have a concept of a global function and a local function. Here's a global function. Global functions just will have their symbol declare global for the linker, so that outside entities can have access to these functions. Local functions, the only distinction is that their labels are not declared as global, so they're only for use within this compilation unit. I have various parameters on functions. Save full context, because this is a context switcher. I let the compiler know, hey, save all the state that's pertinent for my coroutines, which basically is all the true registers of the machine that is in being compiled for. And in the case of the Cortex M4, the link register. If I didn't have that, it would only save the registers that are used within the function, so that I don't clobber them for the caller. And then return says that this function don't save register 0 because I'm going to return a value through register 0. I could also put a trace keyword here, and I have a little tracer that will go line by line and let me step through line by line, so I can debug functions. As I go through line by line, I can print the stack, I can print the values of registers and what's stored at labeled data locations, and it's just a help for debugging. So a little bit about, so I have normal C or C++ style comments are available. And then you can see down here a little bit of the flavor of the language. I'm saying here load register 5 with what's in register 0. So I've got basic load and store, but the load and store, the destination is always a register, but the source can have an elaborate addressing mode applied to figure out where to get the source. In this case, it's register mode, so I'm loading from a register. This maps directly to a move of R5 from R0 in Cortex M4, but I chose to use a different word because in Cortex M4, sometimes you use a move statement, sometimes you use an LDR statement to load a register. Store statement, here's an example. I'm storing register 1. I'm saving loops. The loop, this is, I determined that loop is calling in to kick off running through the coroutine list. and I need to save loop's stack pointer so that when I return to loop, I don't return with the wrong stack active, that I return with its stack active. So here's an example of storing a register at a memory location. So loop SP is one of these declared memory locations. It's like a variable, and I store that stack pointer out there. Because the Cortex M4 has some trickiness about when you can use a stack pointer in an instruction, it's not available with all addressing modes. It's just kind of restricted, and I found that in other machines the use of the stack pointer is restricted. In my language, you're only allowed to do register to register operations with the stack pointer. So I move the stack pointer into R1 and then I store it out. It's a two-step process. There's going to be some compromises. The idea here is I'm going to want to be able to target very different machine architectures. So I'm making some compromises in the language that will show up as some extra operations in that you could do it quicker if you were using the actual machine's assembly language, but this is a compromise. I'll mention that at any point in the code, if you happen to know the target architecture, I have a kind of like an escape code that says from here to here, I'm gonna put inline assembly for the actual target machine. So if you happen to know that you're only ever going to compile this for that one target machine, and you're really only using this for the nice control structures, you could program in the raw assembly language of the target machine. Just there's a keyword that lets me know that you're going to insert raw assembly code. Just to show you, I've got an if with a then clause and an else clause, and then down here is an end if for it. I've got nested. You can nest if statements. So here's an if end if. Here's another if end if nested inside of an else statement. Down here you can see I've got while statements. The Boolean expressions are a little odd if you're not used to what we used to call reverse Polish notation. I don't know if that's politically correct anymore to say that, but it's RPN notation or postfix notation. It just is easier to compile a postfix Boolean expression than a infix expression with a lot of parentheses. It's just easier to write the compiler, so I chose that. So instead of saying, does R3 equal 0, I say R3 0 not equal. Is it not equal? So postfix for the Boolean operation. I don't have an example of any inline assembly here because this code really just moves data around. So I don't really need to do much math. I've got some basic math like add, subtract, multiply, but a thing like this is just moving data around and playing with the stack pointer, which is just a more data movement operations. So that's a little bit of the flavor of, you can see my struct type. So I'm using that node structure and I'm storing R1 at the location of the state entry in the node that's pointed to by R3. So I can treat registers as pointers to structured data types. I can treat registers as raw pointers and just store at the location that the register points at. I can treat a register as an array pointer and store at an index offsetted from the register where the register is pointing. So in a later video, I'll go over all the addressing modes, basically once I write the documentation. But there's some really nice addressing modes that look similar to the modes that are available in the Cortex M4. It's kind of my favorite machine right now, so I chose its addressing modes. But, you know, its addressing modes are similar to other machines like the ESP32. They're very different from AVR. AVR has for, you know, indirect loads and stores, and for indexed loads and stores you use X, Y, and Z registers, which are register pairs, but that will all be hidden by my compiler, and you'll be thinking you're just doing this kind of stuff using a register. Behind the scenes, it'll be using the X, Y, and Z register on an AVR machine. There was something this just popped into my head. When I was saying that, I don't remember what it was, but basically stuff will be done behind the scenes on the AVR processor, because it's very different from other processors which I'm dealing with, which are 32-bit processors, which look a little more conventional. Register. I know what I was going to say. Because I don't know, from a user of the language point of view, I don't know. I should be able to write code and not know what the back end is. That's the ultimate goal, is the same code will compile for multiple back ends and still work. And so I don't know the register model of the back end, because I should be unaware of the back end. The compiler takes care of mapping the language's register model into the true register model of the back end of the actual machine. And so I chose that the language can have any number of registers, and you should just use them in sensible ways. That you start using low numbered registers, R0, R1, R2, and so on. Those will map to the first register, the second register, the third register of the machine. But obviously there could be a mismatch. Some machines might not have enough registers for the number of registers you're using in the code. Well, I do what I call emulator registers. So if I'm on a Cortex M4, which really only has 13 general purpose registers, R0 through R12. If you use R50 in your code, behind your back, it's going to spit out code that emulates R50 in a memory location. And that's all going to work out. Behind your back and seamlessly. So that's enough about the language. Now let's talk about the coroutines, because that's what this video is really about. So coroutine is the base class that you derive from for defining your user level coroutines. And so here we have the header file for coroutine. It has some private methods and data that you won't have direct access to. But a coroutine has 32 signal bits that can be set and reset and used for wake up purposes. And then I've got some private methods. By the way, those methods that I was showing you in Yeah, those methods that I was showing you in the assembly code, the SHLA code, those are implementations of members of the C++ class, methods of the C++ class. And the only magic required there is to know that they're gonna, in the case of a normal method, it's gonna be passed this pointer in R0, and the name of the method is gonna be mangled, so I need to do some sleuthing to figure out how the compiler is gonna mangle the name. If you don't know about name mangling, you can look it up on Google. In the case, one of my methods is a static method. In that case, it doesn't get passed to this pointer, but the name still gets mangled and I have to deal with it. But anyways, that's not stuff that the user of coroutine needs to know. All you need to know is there's one virtual method called main, and you implement main. That's your coroutine, and everything happens seamlessly behind your back. There's a public method of all coroutines called set signal bits. Anyone can call this if they have if they have a pointer to a coroutine object. They can call this to set signal bits, and if the coroutine is waiting for signal bits to wake up, they will get woken up on the next cycle. I have these protected things, which are the various ways, various methods that are available to a coroutine. The first ones here are for various ways to yield. You can yield for a sleep time in milliseconds. You can yield waiting for signal bits. You specify a bit mask to say which bits you're waiting on. And if any of those bits get set, you will be woken up. You can yield until a function is true. You pass in a pointer to a bool function that takes no arguments. So, you may need to do some finagling to make that work for you, but in a lot of cases, that's all you really need for self-signaling, some other thing signaling you. It came in handy for my thing that needed to wake up when there's keyboard input. And a coroutine exit, so that you can gracefully exit a coroutine if you decide to terminate your coroutine. If you fall off the end of main method, you will also exit, and you can also exit some other coroutine. If you have a pointer to them, you could cause them to exit. This just is, there are programming instances where you might want to kill another coroutine, and so that's a feature that's available. There's another argument on all the yields, which is yield to coroutine, and what that means is, do the yield as normal, depending on what type of yield it is, but please, on a priority basis, as soon as I yield, wake up this other coroutine that I am providing a pointer to, if he is ready to wake up. So it's just a way to get a coroutine shuffled up in the order. Normally, there's a set order that I go through as coroutines yield, but you could say, hey, do this one out of order, and it can be used by a coroutine who's waiting on signal bits. That's the main purpose of it, that if you're going to signal a coroutine, you might want to say, hey, I just set their bits, wake them up on a priority basis so that they can wake up and respond to the bits I set. There's another method down here, signal bits, that a coroutine can call on themselves to see the current state of their signal bits. So if they were waiting on signal bits, when they wake up, they can check the signal bits to see which bit got set, so they know what to do So you're allowed to have 32 signals, like, which may seem excessive, but that's the word size here. So I said, why not have 32, right? Clear signal bits so that you can clear a bit once you respond to it, so that you don't get woken up again the next time you wait on that bit. You can clear the bit, and that will cause you to wait again until it gets set next time. Okay. There's a constructor that you can call to set your stack size. Most of the coroutines are simple that I've been writing. 1024 bytes for a stack seems to be fine. That might seem big for some smaller processors, but for a Cortex M4, it's not bad. There's a lot of RAM in a Cortex M4. I've had one coroutine that needed more than 1024, and you can certainly use less. And on machines that have smaller RAM, they tend to use less stack anyways, so you can set the stack size smaller. And then there's a static method, yield from loop. The idea here is that loop will, I'll show you an example, but loop will call at the top of loop yield from loop. So loop will yield to the coroutine kernel, which will allow it to run through its list of active coroutines, activating them if they're runnable. And when it's done going through that list once, it returns to loop, lets loop do its thing, and then loop can call in again the next time. It's a way to allow loop to still operate while coroutines are operating. In other words, loop is a special coroutine, but the only kind of yield it can do is a yield for no milliseconds. That it will yield just a pure yield. Go ahead and do other coroutines, come right back to me next time through the loop. In the case of yield for milliseconds, if you say 0 milliseconds, all you're really doing is saying, wake me up the very next time you run through your list of coroutines. So that's kind of what the yield from loop does. It's treated specially because the yield loop is not in the coroutine, not a coroutine class. It's a special thing. It has the system stack pointer, and so it needs to be treated specially. And so I have a special function for it. So here's an example of coroutines. Here's a coroutine I call one-shot coroutine. All it does is define, so it says I'm a child of coroutine, and it defines main as just printing out a message, one-shot coroutine got called. And so when it gets activated, all it's going to do is the first time it's activated, it's going to print out that print statement, fall off the end. It'll get removed from the list of active coroutines because it fell off the end, and that's essentially an exit. Here's a coroutine that will exit after 10 seconds. So it defines main as it'll print out exit after 10 seconds started. It's going to yield for 10,000 milliseconds, and then it's going to print that it's exiting. And so this is a simple coroutine that just yields once and then exits. Here's a coroutine that yields every n seconds. So it's an example of how you can make this a little bit variable. Its constructor takes a string so that you can name it. This is just for nicety, so I can watch these coroutines get activated. How many seconds per sleep time, and basically their main says it'll loop forever. It'll sleep for that many seconds, so seconds times 1,000, it'll yield for that. and then it'll print a message, they woke up, and then it'll go around the loop and sleep again. These are just examples of simple tests of coroutines. Here's a routine called ever yielding coroutine. It's an example of yielding with no timeout. It just means I'm yielding now because I'm being nice. That's how you would use it in actual practice. You don't want to sleep, but you want to give other coroutines a chance to operate. So you just do a yield that will cause you to remain runnable. And so the next time through the coroutine, as it's going through the coroutine list, it'll activate you without a delay. Here's a coroutine that waits for keystrokes. So here's an example. Here's a Boolean function that just returns the value of serial.available. Okay, so, and it returns it as a bool. And this coroutine says yield till func true, and it passes a pointer to that Boolean function. And so it'll only wake up and say got a key whenever a key has been pressed, and then it reads the key and prints that out. So that's an example of how to use wait for a function. Here's one that's waiting for a signal. So it's while true, it's going to stay in this loop, and it says yield for signal bits, and it's passing 3 in hex, which means the low order 2 bits. If either of those get set, that's the signal mask, is if either of those 2 get set, I want to wake up, and it clears, in this case, it clears both bits. It could have inspected its signal bits to see which bit got set and just cleared that one. But this is just a test program, so it clears both bits. And then it prints out that it got a signal, and it goes and waits again. Here's a routine that would signal it. So every 5 seconds, so it's going to yield for 5 seconds. It's going to wake up, and it's going to set the signal bits, signal bit 2. So the second lowest order bit, and it's in the other routines signal bits, and that will cause, if he's passed in his constructor a pointer to one of these other guys that's waiting for signal bits, he'll wake them up if they're waiting. Here's an example of a priority wake up. This just says in a loop, yield for 10 seconds. By the way, wake up this other coroutine that was passed to me in my constructor, so that he gets woken up on a priority basis. And it's an example of doing it after setting signal bits. So what he does is, let's say the other guy is waiting on signal bits. This guy goes to sleep for 10 seconds. He says, wake the other guy up on a priority basis, but that guy hasn't been signaled yet, so he stays asleep. 10 seconds pass. This guy says, well, set his signal bit, and goes to sleep for another 10 seconds and says, hey, wake that guy up if he's waiting for signal bits. He is waiting for signal bits by now, and he will wake up on a priority basis. Here's an example of how to exit another coroutine, but basically all it does is call coroutine exit, given a pointer to another coroutine that's executing. If that coroutine already exited, no problem. This will just be a no-op. It won't hurt anything. And that's kind of a run through of what you can do with these coroutines. And someday I'll show the code for the experiment that this was all written for. So the random number experiment, where there's actual coroutines that do things, but also use these features of the coroutine class. So that's all that I want to show for now. Thank you for listening, and especially if you watched the whole video, you're great. I mean, to pay attention for that long, and I hope to get this stuff released so that people can use this in their own programming. So see you next video.